Hi, in this video we are going to see about applications of operational amplifier. So we know that operational amplifier is widely used in analog circuits. So some of the applications of an operational amplifier let us discuss here now. Applications of an amplifier is broadly classified into three different categories, that is the linear applications, non-linear applications, and it can be also used in a wave shaping circuits. Linear applications means the output of the circuits depends linearly on the input. So those structures are some of the examples of a linear thing, that is the scale changer and a sign changer circuits, adder, subtractor, instrumentation amplifier, integrator, differentiator, and log and anti-log rhythmic amplifier. Whereas non-linear means output does not depend linearly on the input, whereas in some conditions of the input, output changes. So this is what a comparator circuit based on the output, based on the input, the comparator output will generate the output. So zero crossing detector, amplitude analyzer, window detector, Smith trigger, clipper, clamper circuit, sample and the hold circuits are some of the examples of nonlinear operational amplifier applications. Whereas a wave shaping means from the name wave shaping, so it is used to generate the different types of waveforms, that is a sine wave generator, a triangular wave generator, and the stable multivibrator, it is a square wave generator, and monostable multivibrator pulse generator. Bistable multivibrator is also used, also can be designed using a operational amplifier. And next thing, here this is what a basic application of an operational amplifier, where the op amp has a two input terminals and one output, where the uh, here we are having a negative feedback in an operational amplifier. We know what is the reason for using a feedback in the operational amplifier: to avoid the that is to improve the applications of an operational amplifier. We have made this feedback of an output to the input side. Using this, there are so many applications we can done using this negative feedback. So now we are having a feedback resistor and a input resistors, and one of the terminal is grounded in an op amp. So we are going to give the input for the inverting operational amplifier terminal. So the name of this amplifier is an inverting amplifier. So what is inverting amplifier? Which produces the output. Since we are giving an input for the inverting terminal, the output is the 180-degree phase shift of the input. So this is what we are having. We know that in a basic operational amplifier, this is grounded due to ritual concept. This VB is equal to VA. So VB is equal to 0, where VA is also equal to 0. And also here we have there is no base current to that of operational amplifier. So IB value is also equal to 0. So now VA is equal to 0. IB negative is also equal to 0, and we know some of the networking laws, that is a Kirchhoff's law, current towards the junction, away from the junction. So using those we are going to find the output of an op amp. So first we consider what is the current I1. So that is a current I1 is across this resistor. For this resistor, two potentials are available. So from this current direction is from Vin to Va. So Vin minus Va divided by R1 is your current I1. So simplifying this, Va equal to 0. So simplify this, we will get Vin divided by R1. Similarly, what is IF? IF is also has a two potentials, Va minus of V naught across the resistor RF. So Va equal to 0. So it is equal to IF is equal to minus V naught divided by RF. So here IB equal to 0. So towards the current, applying a KCL, we will get I1 is equal to IF. So equating the I1 value and IF value, we will get a relation between input and output. So the output value is equal to minus Rf divided by R1 into Vin. So from this we can see that output is the negative value of a input, that is, this indicates the 180-degree phase shift. Output is an amplified output from the input, but it is 180-degree phase shift. This is what here we are having output. It is exactly inverted here, so its phase shift is 180 degree. This this is about an inverting amplifier. Next, the same circuit, only change here is in previous circuit a positive terminal is grounded, whereas in this circuit negative terminal is grounded and positive terminal is given as a input. So here that we are giving an input for the non-inverting terminal of an op amp. So the name of the circuit is an non-inverting amplifier. So this non-inverting amplifier will not produce any phase shift in the output. So it is both our input and the output are in phase to each other. So here also the same thing. We know that VB is equal to Vin since we are giving an input for this terminal. So as usual, there is due to ritual concept, VA is equal to VB. Since VB is equal to Vin, VA is also equal to Vin. Here it is grounded. Here also we are going to find I1 current. So from this potential to this potential, so the same thing we are applying here in non-inverting also. I1 is equal to VA minus 0 divided by R1. Simplify this, we will get I1 is equal to Vin divided by R1. Similarly, what is IF? IF is equal to, from this potential to this potential it is moving. So V0 minus VA divided by R1. So here we got the value V0 minus VA divided by RF. So here also the same thing. There is no current towards the op amp, so whatever the current here we are receiving, it is forwarded to I1. So I1 is equal to IF. Equating these two equations, we got a V0 in terms of Vin. So this is what a derivation for it, where we are having a V0 is equal to 1 plus RF divided by R1 into Vin. So here we can see there is a no negativity. It indicates there is no phase shift, whereas output is equal to 1 plus Rf divided by R1 into Vin. So only the amplification factor, this 1 plus Rf divided by R1 is the amplification factor for non-inverting operational amplifier. So from this diagram we can see this, both input and output are in phase to each other. It is amplified. Output is amplified with respect to the proportionality concept, that is a amplified gain due to RF and R1 resistance. And next circuit is we can see that there is no feedback resistor and also there is no input resistance. So the input is given for the non-inverting terminal, input resistor and feedback resistor both are not available. So this circuit means we are giving an input for the non-inverting, that will be forwarded to the output, that is fed back as a input. So what we are getting, it is feedback, so that is what it follows the voltage we are giving in the input side. So the name of the circuit is an voltage follower. There is no gain in the circuit. This is also called as a buffer and it is also an isolation amplifier. The circuit in which output follows the input, it is called as a voltage follower. So what is the how we are telling that VB is equal to Vin, whereas VA is equal to Vin. So here V0 is equal to Vin. From this feedback, V0 is equal to Vin. So V0 is equal to VA. So hence there is no gain in the circuit. It is a unity gain circuit. What is the advantages of it is, it has a high input resistance, low output resistance, large bandwidth, and the output follows the input exactly without any phase shift. So wherever we are in need of a large input resistance circuit, there we can use this buffer. This is what application of an voltage follower, and here we can also see the same thing. There is no increase in the, that is amplification in the output. The same input with the same phase we are having received in this. And next, a small thing is a scale changer. So from the circuit we can see this is what an input scale. Here it is a negativity or positivity. So the input is given for the inverting terminal. So the output is equal to, already we know that this circuit is an inverting amplifier. V0 is equal to minus RF divided by R1 into Vi. So here if R1 and RF is equal to 1, what happened? V0 is equal to minus V1. So here the based on this R1 and RF, the scale of the output changes. So the name it is a scale changer. If the R1 and RF value equal to 1, this circuit is called as an inverter. Thank you.